Yes, good afternoon and welcome to the lecture of say basic electronics, analog electronics, in which we were studying the basic laws of the basic laws of circuits. And yes, of course, uh, yeah. So we'll be continuing that what we have studied in the last lecture. So let me share my screen on that, and we'll continue with that. So yes, yeah, this is that. I guess my screen is visible to you. So let me introduce myself. Myself, Dr. Andy Mishram, Head and Associate Professor, Department of Electronics, Sri Mathura Das Mohta College of Science. And we are going to continue with the basic laws of electronic circuits, right? Yeah, in the last class, I guess we have studied uh, some of the basic laws of electronic circuits, in which I told you some definitions of linear elements, non-linear elements, and active elements. Similarly, passive elements. So I have shown you, explained you all these components, and then we have completed unilateral elements, unilateral components, bilateral components, and voltage, ideal voltage source, ideal current source. What is resistance? I guess we have almost completed this. So, and we have started with Ohm's law. So we have done with this. He is George Simon Ohm, who was the inventor of Ohm's law. Hopefully, the he has given the law that the voltage across a resistor is directly proportional to the current flowing through it. So this was there. Then we have studied this Ohm's law with related to power, and then we have done this graph which shows a linear relation between voltage and current, which shows that the voltage is directly proportional to the current, and it is shown by the straight line. So yeah, we have completed all those things. So about resistance, yeah, this is how we calculate the resistance uh, of a material. So in which we have a formula R is equal to rho L by A, where R is the resistance, specific resistance in fact, and rho is the resistivity per unit per meter of that material. L is the length of the conductor, and A is the cross sectional area in meters. So this was how we calculate the resistance of that. Then we have studied about the reciprocal of resistance, that is conductance. And I guess we have completed this example. Then yeah, now today we have to continue with this. What is uh, what is that? What is called as a node, right? Whenever we talk about a circuit, then this is an important parameter which is concerned with a circuit, and that is called as a node. Now, what is a node? Any point where two or more circuit elements are connected together. So any point, I guess. I'll show you in this example. So node is a point where we are expecting that two components are going to be joined, two or more components are going to be joined at a one point, and that particular point is called as a node. This is very important, so remember this. Then wires usually have negligible resistance, means the wires which we are taking it for connections, they have a very small resistance, very low resistance, so they are very negligible, so we won't count the resistance of those wires. And each node has one voltage, so one node will have its own respective voltage with respect to ground, right? Then we have the another term that is related to circuits. Those are called as a branch, a circuit element between two nodes. Now, between two nodes, whatever circuitry we are having between in that two nodes is called as a branch. And the third one is the loop. So whenever we need to have to complete one circuit, we need it to complete from the positive to ground, right? The circuit is to be complete, and that we call it as a loop. So this is actually the collection of branches, right, that form a closed path returning to the same node. So we are returning to positive to ground again to that same particular point, and that particular form of branches is called as a loop, right? So I'll read it for you. A collection of branches that form a closed path returning to the same node without going through any other nodes or branches twice, right? So that particular is called as a loop. So these three are very, very important as far as the basic electronics are concerned. So examples, now let us try these examples. How many nodes, branches and loops are there in this particular circuit? So this is a small circuit in which this Vs is supposed to be the voltage source. This Vo is supposed to be the current source. This is the symbol of current source, that is an arrow inside a circle. So this is the current source and this is the voltage source. These are resistances R1, R2 and R3. And if you are able to see, the positive of the voltage source is connected to resistance R1, whereas the second end of this resistance R1 is connected to R2, R3 and the current source. So these are all connected. So when we take in terms of nodes, these point where it is connected, R1 is connected to R2, R3 and say the current source, this is taken as a node, whereas this resistance, the component which is connected between these 2 points is called as the branch. And this forms a loop. So when we start from the voltage source Vs, so Vs, R1, R2 and again to Vs, so it will complete one loop, right? So in this circuitry, how many nodes, branches and loops are present over there? That is what we are expecting to calculate now in this section. So let us try this in this. How many nodes are there? So let us try how many nodes are there. If you can find out, let me tell you how many nodes. There are only three nodes. Now how these three nodes are being calculated, let us see. So this is 1 point. This is the whole of this is the second point, that is called as the second node. And this is, since it is connected to all the terminals, so we are taking it as the third node. So in all, in this circuit we are having three nodes, means we can take in terms of 3 points, right? So we are having three nodes over there in this circuit, and this is how these nodes are being shown. So this is the one, this is one node, and this is the second node, and this whole is the third node. So we are having three nodes in the circuit. Now how many branches are there? So let us check for branches. So branches are, five branches are there, and these are shown over here. See how branches are being defined. So the components or the elements which are connected between the two nodes are taken as one branch, right? So the voltage source is connected over here in between these 2 points. So this is one branch. This is R1 is the another branch. R2 is third. R3 is fourth. And the current source is taken as the fifth branch. So these are the branches. And if we talk in terms of loops now, let us find how many loops it is having. I guess you are understanding this, what I need to tell you. So in this circuit, there are actually three loops, right? So if we starting at node A, so A, B, and C are the three nodes over there. 1, 2, 3, 4, and 5 are the branches. And now when we talk in terms of loops, so we need to know how many times the circuit is being completed between that particular loop, right? So in the first loop, when we take A, B, and C as the three nodes, the first loop will be like this. So voltage source Vs, R1, R2, and again back to Vs. So this is first loop. Second loop will be Vs, R1, R3, and back to the Vs. That is the second loop. And the third loop will be Vs, R1, the current source, that is Vo, and back to the voltage source, that is Vs. So this is how three loops are there in this particular circuit. So this is how we can calculate or say, uh, this is an example where we can actually find out how the loops and nodes are being defined, and why how are the branches are being defined over there, and how we can say that there are these branches. So A, B, C are the three nodes, and Vs, R1 and R2 is the first loop. Vs, R1, R3, and again Vs is the second loop. Vs, R1, and the current source, that is Vo, and back to Vs is the third loop. So this is how we can calculate the loops, branches, and nodes. I guess you have understood. If you have any problems, kindly let me know. So yeah, this is the another law which we call it as the Kirchhoff's laws. These are very important, which we need to study in this section. So Kirchhoff's current law. So Kirchhoff's current law, as you have studied in your 12th, the sum of the current entering a node or a node or a junction point equal to the sum of the currents leaving the junction. Current entering the junction, current entering to a node is equal to current leaving to the junction, right? So remember this, at a point, how many currents are reaching over there and how many currents are leaving from that node are should be same, are equal, right? For example, if you are seeing this diagram, so IA is entering to this node, IC is leaving this node, ID is also leaving this node, and IB is also entering to this node, right? So these arrows shows the flow of current, right? So in this case, we can have an equation where we can say that IA plus IB, these are coming towards the node, so we are taking it positive. So IA plus IB must be equal to current leaving the junction, that is IC plus ID. So IC and ID are the currents which are leaving the junction, whereas IA and IB are the currents which are entering the junction. So this is how the Kirchhoff's current law is being say defined, that the current leaving the junction should be equal to current entering the junction, right? So this is how I have shown you. So IA, IB are entering the junction, so I have taken IA plus IB, and that must be equal to IC plus ID, right? So yeah, IA, IB, IC, and ID can each be either a positive or negative, depending on how you take it. So if you take this IA and IB entering to the junction as negative, then IC and ID should be taken as positive. If you see this equation, IC, if you remove this IC and ID take in the on the left hand side, then IA plus IB minus IC minus ID must be equal to 0. That gives you the another definition of current Kirchhoff's current law. That is actually the sum of the currents at a node is equal to 0. Sum of the currents, yeah, summation of the currents at a node is always equal to 0. This is another definition of Kirchhoff's current law. So can we try some examples on that? So let us try this example of Kirchhoff's current law. This is what I have told you. The algebraic sum of all the currents entering a node equal to entering or leaving a node is equal to, yeah, at a node is equal to 0. So this is how I have told you that IA plus IB minus IC plus ID. So if you see here, they are different now. So IA is entering the junction, ID is also entering the junction, IB is also entering the junction. So I have taken IA plus IB plus ID. Whereas since sorry, so in this equation, yeah, IC is entering the junction, but it is minus. So I have taken it as minus. So summation of all the currents is equal to 0. They can be positive, they can be negative as well, right? So yeah, this is Kirchhoff's current law. The algebraic sums of currents leaving a node is equal to 0. Now here IB is taken as minus, so IA plus IB plus IC, sorry, IA plus IA plus IC plus ID minus IB is equal to 0. So that is the another equation that we can write over here in this form. So yeah, uh, just hold for a second, I guess. Uh, okay, so uh, just for a second. So we are here now. Yeah. So this is one more example I need to show you where I could find this. Yes. So this actually I need to show you this example. So this is there. Uh, this is a node which is shown in square, and these are some of the currents. 4 ampere is the current entering the junction. 2 ampere is the current coming to the junction. 6A is also coming to the junction. This is minus 1A, which is actually leaving the junction. So we have taken it in the negative direction. 9A is another current leaving, coming to the junction. So this was how we were expecting to calculate. Now, what would be the current which should come out of this node and which can be named as IX, right? So what should be that current? So that is to be calculated. So this is how. we were expecting to show you. I guess it is visible now. So yeah, I will just make it a bigger one. Or I can just push it this one to, yeah. So that yeah, is it visible now? So yes, this can be shown. I will switch it again. Yeah. So this is the another example of that. We need to find this is a circuit in which there are currents flowing through this, and we need to calculate the currents IW, IX, IY, and IZ. So yes, I guess it is visible to you. Uh, so these are the currents over here, and we need to calculate Ix, Iy, and Iz. So what would be the Iw, which is supposed to leave from here? So we can calculate the currents through here, and accordingly we can say that the current is okay. Uh, yeah. So the current flowing through IW is minus 2 ampere. Now this is how we have calculated. Since current leaving the junction is taken as 2 ampere over here, so here also it should be 2 ampere, that is minus 2 ampere, and this is the whole circuit. So current, whatever current is coming out from here should leave from here. Yes. So this arrow is actually opposite. This should be entering the junction, and this should be leaving the junction. So since it is taken positive, it is taken negative. So minus plus 2 ampere. This is the current which should be positive, I guess. So yeah. So this is positive, and the arrow should be inside it. So this arrow is opposite. So it is entering this circuit, and this is leaving this circuit, IW. So the same current should leave. So 2 ampere is the current which is entering this circuit. So IW is leaving the circuit. That is why I have taken it minus 2 ampere. So this is taken as positive, and this is taken as minus 2. Again, what would be the value of Ix now? If you calculate accordingly, you will find that this whole current, this 6 ampere, is going to be divided into two parts, right? So IAY and IX, sorry, this 9 amperes. So again, this is divided into two parts like this. So what would be the current? That is what is shown over here. Yes, okay, so it's not showing right now. So, okay. So I'll just show you this. So this was the current here, and then for current XY, uh, yes, minus 5 ampere should be the current flowing through IX. So just see this how we are going to calculate, and what should be the current flowing through IY. So IY should be minus 3 amperes. So total minus 3 minus 5, that is minus 8 amperes. So IZ must be minus 8 amperes, right? So this is how we are going to calculate this. These are some of the examples. Now for this, so yes, so Kirchhoff's current law can be generalized to include a surface with which we assume the elements within the surface are interconnected. Now this is a closed 3D surface, and they are enclosed, the elements are enclosed inside it. So the currents which are coming towards this are leaving this junction, and the summation remains to be zero. We can now apply Kirchhoff's current law in three forms we discussed with notes. The appearance might be as follows. So it might appear like this. So here inside it, we are having a circuit like this, any resistors belonging to them, and we are having four lines which are coming or getting inside it. So this is inside coming inside, and these are leaving this closed surface. So currents entering and leaving a closed surface that contains interconnect circuit elements. Then the second law is the Kirchhoff's voltage law, that is KVL. The algebraic sum of voltages around a loop, around each loop, is zero. And beginning with one node, add voltages across each branch in the loop. So this is how we can calculate. Uh, so positive and negative signs can be given accordingly. So summation of voltage drops minus summation of voltage rises is equal to zero. So summation of voltages in a loop are the summation of voltages in a loop is equal to zero. So voltage source positive to negative, that is taken as positive, and from negative to positive, that is taken as negative, right? So all this can be taken as equal to zero, right? So summation of voltage drops is equal to the summation of voltages rise. Means whatever voltage source we are applying, the total voltage it should be equal to the voltages which are being dropped across these elements. That is to be taken as the summation of both them, and they should be equal, or say the voltage drops across in the loop is equal to zero. So this is how we can analyze the circuit. When a given circuit with the sources and resistors having fixed values, you can use Kirchhoff's two laws and Ohm's law to determine all branches voltages and current. Now if this is a simple circuit, we are having a voltage source and we are having two resistances over here. So we can use a simple Ohm's law to calculate the current flowing through that. Since 7 plus 3, that will give you 10 ohms, and it is connected in that circuit. So 10 ohms can be, the current through this circuit can be calculated simply by using Ohm's law. But yeah, this is how this has been shown over there. So yeah, so this can be taken as the voltage across this resistance, across 7 ohm resistance, and then voltage across this 3 ohm resistance can be taken. Yeah. So this is the simplest one where we can identify and we can calculate the current, how much current is going to be flown through this circuit, right? By using just Ohm's law. So this is simple. But when we try in terms of say KVL, so we are having VAB plus VBC minus 12 volts. So we are taken this voltage drop as positive and this voltage source as negative. We can interchange it also, and that should be equal to zero. So substituting this values over there, so this is not the actual over there. This should be the current flowing through that. So no, this is the voltage. So yeah, so I guess I into I dot 7 ohms, है ना? So I is the current, I 7 ohms plus I dot 3 ohms. This is the multiplication. So I into 7 ohms plus I into 3 ohms minus 12 volt will give you 0. So I, if you take it common over there, then we'll be having I into 7 plus 3, that is 10 ohms, right? 7 plus 3, 10 ohms minus 12 volt is equal to 0. And if you calculate the current by that equation, you'll be getting 1.2 amperes. That is actually the current flowing through this circuit. So this is how we can calculate a simple by Ohm's law. Also, similarly, we can calculate by KVL also. So in Ohm's law, we'll be calculating like 7 plus 3, that is 10. And the total resistance is 10 ohm in this circuit, and the voltage is 12. So V equal to IR, I equal to V by R. So V is 12 and R is 10. So 12 divided by 10 will give you 1.2 amperes, right? So this is how we can calculate directly by Ohm's law. But by using, say, the KVL, the voltage drop across VAB, the voltage drop across VBC. So these are to be added minus 12. Since we don't know the current, so I into 7 ohms plus I into 3 ohms minus 12 volts. So this is also a voltage, this is also a voltage, VAB and VBC. Yeah, and we can calculate accordingly. So still the voltage will be 1.2 ampere. Now this is the simplest circuit where we can say it like this. But when we have a complicated circuit like this, now how you are going to calculate the current flowing through the circuit? So in these situations, we require some theorems to calculate the currents flowing through these branches, right? Or say Ohm's law is a little bit complicated to solve these sorts of equations. If you go on solving this, so we'll have a different sorts of arrangements like. So 6 plus 4, these are in series, but 6 plus 4, this resistance, this whole resistance is in parallel with 8 ohms. So we have to calculate the effective resistance of this, and then we have to add this, and again we have to calculate the current flowing through that. Then we have to separate this, and again we have to calculate. So this is how this procedure is a little bit complicated if you start using Ohm's law itself, right? So we need some more theorems for that, and for that we have these network theorems. So we'll try this by Kirchhoff's voltage law only. So let us try this using Ohm's law at polarities. So this is there I1 plus I1 into 10 ohms. So this is the one voltage. Then this is the another voltage, that is I3. Then this is I3 again. This is I2 we are taking. So I3 into 6 ohms, I3 into 4 ohms, and this is I2 into 8 ohms. So this plus this plus this and plus this should be equal to this. So this is how we can calculate like equation like this, by taking Kirchhoff's voltage law equation in this loop only. So we'll have this only for this loop. We'll be having this equation. First, Kirchhoff's law, voltage law, and say for the another loop we can have, this is for one loop, and for another loop we can have the another equation like this. So this is for the another loop. So this is second Kirchhoff's voltage law will be like this. So we are having another loop like this. So we want a I2 dot I2 multiplied by 8 ohms plus I3 into 6 ohms plus I3 into 4 ohms, and that is equal to 0. Now the current is reversed, so we are taking it in minus. So minus I2 into 8 ohms plus I3 into 6 ohms, and like this. So this equation is this is how we can take this equation, and I2 dot multiplied by, similarly we can take this like we can solve this equation, we can use this. I expect that this is visible to you. This is slightly in light color, but I guess it is visible. And this is by using this equation, Kirchhoff's voltage law, we can calculate the currents flowing through all I3, I2, I1 can be calculated accordingly. So yeah, so these equations can be summed up like this, and accordingly we can solve these equations by using KVL. So these are some examples of it, how we can solve it, and the whole is given over there, and we can say that these are the current voltages which are there. So I guess this is okay for today now. We'll be continuing this. So Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is current entering to a junction is equal to current leaving the junctions, or the current at any node is equal to zero. The summation of currents at any node is equal to zero. This was the Kirchhoff's current law, and the other one was the Kirchhoff's voltage law, that the summation of voltages in a loop is equal to zero. Summation of voltages in a loop is equal to zero, right? So that we have taken here the example of this circuit, and here we have tried to calculate by using the Ohm's law and Kirchhoff's current law, right? So yeah, we have analyzed the circuit like this, and we tried to calculate. Yes, this was the simplest circuit. This was a little bit complicated, and here we need to calculate I1, I2, and I3. So this is how we can calculate over here. I1 can be taken as I1 multiplied by 10 ohms, I3, I2 multiplied by 8 ohms, and we can calculate the currents I2 and I3 accordingly. So this was the simplest equations that we got in one loop, and this was for the another loop where we are not having any voltage source. So this was the second loop, and we can write this second Kirchhoff's voltage law like this. Yeah. So yeah, we can write like this, and yes, so we have this equation. So I1 is equal to I2 plus I3, or we can take it I1 minus I2 minus I3 must be equal to zero. Summation of all the current, that is Kirchhoff's current law, can be employed over here, and we can substitute that in the first equation so that we can calculate one of the currents, and we can find out the other currents by using these equations. So these are some of the simplest methods where we can calculate. So I3 is 1.538 amperes, uh, I2 is 1.25, and yeah, I3 can be calculated as 1.25 multiplied by I3, that is 1.923 amperes, and I1 is the addition of I2 plus I3, so I1 must be 3.461 amperes. So this is how you can calculate it, and these are the say the voltages drop across the resistances: 10 ohms, 8 ohms, 6 ohms, and 4 ohms. The total voltage across this loop will be 50 volts only. So this is how we can calculate the Kirchhoff's current as well as voltages across the resistances by using this Kirchhoff voltage law and Kirchhoff current law. I guess you have understood this. And if you have any questions, you can ask me right now. So, are there any questions? Hello, anyone can unmute themselves and ask questions. So, okay, I guess you have understood. So, thank you very much for uh, attending this class. Thank you, Sanket. And yeah, so I will be continuing and I will be rushing up to complete all the syllabus at the earliest. So we have very less time to go because thank you very much. Stay home, stay safe, and take care. See you soon in the next class. Good day. Have fun. Bye.